Hello, good day. Today's lesson is all about phase change, and this is one of the topics under the midterms. Let's start. Our lesson objective for today is to explain what causes matter to change state, compare and contrast different phase changes, describe the role of energy in phase changes, and understand real-world applications of phase changes. So this is just a short skit about our topic for today, but since we are not in-person meeting, we are not in an in-person meeting, and that's why what you're going to do now is to just read the following script. A brainy friend, two friends are in the library. Charlene in a soft voice, Ayo, I was wondering if you could explain latent heat to me. I've been reading about it in my textbook, but I don't really understand it. Annie, sure. Imagine a block of ice is like a bunch of tiny particles, all stuck together in a solid state. Now, what do you think will happen if we add heat to it? Charlene, I guess it will start to melt and turn into water. Annie, yes, that's right. But here's the interesting part. While the ice is melting, its temperature will remain constant at 0 degrees Celsius, even if we keep adding heat to it. Charlene in a loud voice, wow, that's really cool. And the librarian comes in, hey, shut it. So, based from this short skit, we'll have an overview already of our topic for today. Think about the last time you made a cup of coffee or tea. The steam rising from your cup is an example of a phase change. Phase change, in this case, is when liquid is turning into gas. Liquid in the coffee, the water in the coffee, is turning into steam, which is a gas. But have you ever wondered why it happens? Let us explore. So what do you think happens at the molecular level when a substance changes phase? We're talking about at the molecular level. We're talking about the bonds existing between and among the particles of solid, liquid, and gas. Can you think of other everyday examples of phase change? Okay. So let's talk about the states of matter first, before we talk about how phase changes happen. There are 3 most common phases of matter in this planet, but we'll add 2 more later. Let's start with solid, and we will differentiate these 3 phases of matter in terms of arrangement of the particles in matter. Does it have a fixed shape? Does it have a fixed volume? Or can it be squashed or compressed? So let's talk about solids. Solids, particles of solids are rigid. It means the particles have no spaces in between or among the particles. Next one, solids have fixed shape. It means that if you place a solid object wherever you want it to be. For example, if you want to place solid particles, coins for example, in your pocket or at the table or on the table or in every place possible, it will not change its shape. It has a definite shape. Another thing, since there are no spaces in between and among particles of solid, it has a fixed volume and therefore it cannot be squashed anymore. Remember volume in your previous classes? Volume is the space occupied by an object. In liquid, the particles are not rigid. There are a little bit of space in between and among the particles of liquid, and therefore, liquids have no fixed shape. It means that it follows the shape of its container. Another thing is, just like solids, liquids have fixed volume. It means if ever you have, let's say, a liter of water, if you place that liter of water or 1 liter of water inside a pitcher or a basin the volume of the water will not change, and therefore liquids cannot be squashed. The third state of matter is gas. Gas particles are not rigid. It means there is a there is a big space between and among the gas particles. And just like liquids, they have no fixed shape because of these spaces. And also as a consequence of big spaces, gases have no fixed volume. It means you can squash or compress gases. Just like, let's say, helium inside a balloon. You can actually change the volume of the balloon just by compressing it or lengthening the balloon. But there are another states of matter existing here in our planet, but you might think that this state of matter is not very common, but actually it's a common state of matter because it is observed everywhere, and there are many natural phenomena that are manifestation of this state of matter. And I'm talking about plasma. Plasma is a superheated gas. It's just like a gas, but it exists in a state where temperature forces the particles of plasma to become ionized. Ionized means the plasma particles have charges, in particular positive and negative charges. A good example of plasma is the star. Every star in the universe is literally balls of hydrogen, and every second, two hydrogen atoms, two hydrogen nuclei, are forced to become a new element called helium. In the process, it exudes a very hot energy, and as a consequence, it exudes a hot gas. That hot gas is helium, and in this case, this is not just like any ordinary gas, but it exists in a state called plasma. So aside from the sun and every star, lightning is also a manifestation of plasma. When electricity flows through the air, the gas in our atmosphere or the air itself is become ionized as a consequence of a high energy flowing through it. Another common example of plasma is, of course, our fluorescent lamps, our incandescent bulbs, for example. Inside that bulb or lamps are gases, mostly noble gases. But when you turn off the lights or lamps, these gases would become plasma. A fifth state is called Bose-Einstein condensates, or simply BEC. BEC, this is composed of super unexcited. In chemistry, when we say unexcited, this means that the particles in BEC have very low energy, and they exist in super cold conditions, and that's why sometimes we call it super cold atoms. And the temperature required for BEC to exist is the temperature should be near absolute zero. Absolute zero, we haven't discussed this yet, but for advanced lesson, absolute zero is 0 Kelvin. That is a hypothetical temperature where no energy would exist. Bose-Einstein condensate, it has been proposed to exist in 1995. It has been proposed to exist by two scientists in the name of an Indian scientist and, of course, Albert Einstein. Satyendra Nath Bose and Albert Einstein, working independently, they proposed the existence of Bose-Einstein condensates, or this simply condensates, in their time. But in 1995, scientists in a controlled laboratory, they have produced the fifth state of matter. So there you have it. You have the 5 states of matter: solid, liquid, gas, plasma, and Bose-Einstein condensates. We don't have a picture or photo of BEC because they only exist in a controlled laboratory condition. And that's why if you search the web for BEC, it would turn out just like this. You can see here the bottom right of our presentation. This is just a computer generated image for the BEC. So I want to add something about the states of matter. We have discussed in our previous lessons, particularly in fluid mechanics, a theory called kinetic molecular theory. One of the propositions of kinetic molecular theory is that particles in matter are always moving. Every state of matter from BEC up to plasma, they are moving. So what other things kinetic molecular theory states about the phase of the states of matter? Well, it adds that phase change would happen only if the thermal energy applied to matter is greater than the energy of attraction among the particles in that matter. Imagine that the particles in solid, liquid, gas, plasma, and Bose-Einstein condensate, they are close or near to each other because of the intermolecular attraction existing between and among the particles. This attraction is measured in terms of energy. In other words, there is a measurable amount of energy existing between the particles of solid, liquid, and gas, for example, and even in plasma and Bose-Einstein condensate. But then, what would happen if we apply an external energy from the outside, to the states of matter, solid, liquid, and gas? So kinetic molecular theory proposes that phase change would happen if that energy, for example, in this case, thermal energy, if we apply thermal energy to solid, liquid, and gas, if thermal energy is greater than the energy of attraction between and among solid and liquid gas particles, then phase change would happen. What does it mean, phase change? Well, in the next slide, we'll explain what a phase change is. So before that, you can see here that we rank the 5 states of matter. Here, take a look at the right side of our presentation. This graph shows us the ranking of 5 states of matter in terms of the energy that they possess. We have it here at the left side of the diagram, Bose-Einstein condensate. It means that this state of matter, among the 5 mentioned, has the lowest energy. Next to that is solid. That means solid has higher energy compared to BEC. And then liquid comes next, and then gas comes next. And among the 5 states of matter, plasma has the highest energy. So that means that if you want phase change to occur, you have to apply a measurable amount of energy to solid, liquid, and gas. For example, if you want solid to become liquid, then you have to apply thermal energy that would overcome the force or energy of attraction between the solid particles. In the next slide, I'm showing you here the phase changes. Phase changes is simply the change in the state of matter from solid to liquid, liquid to gas, and vice versa. So I'm showing you here a diagram. We have 3 states of matter represented here because they are the most common states of matter that we can observe in our environment. We have solid, liquid, and gas. And there are arrows that you can see here in the diagram. Arrows have labels below and at the top of each arrow. So the arrows are pointing from one state to another. For example, from solid pointing to liquid, that means solid is changing into liquid, and then there is a label at the top of the arrow that says melting. The words at the top or the bottom of the arrow is the name of the process of phase change. So it means that when solid changes into liquid, that is called melting. So you can pause this video and read all the names of the phase changes that you can see here in this slide. Let's let's make use of water as our example for this presentation. So for example, solid water is what we call as ice. When ice changes into liquid water or simply liquid, we call it melting. When liquid water changes into gas, the gas phase of water is called steam or water vapor. So water vapor is the gaseous form of water. The process is called vaporization. But so far, I'm just showing you the forward process, meaning from left to right and to top. But there are also processes that what we call as reverse processes, going from top to bottom to the left. So we know that phase changes are reversible. So phase changes are reversible. Reversible means you can change it back to its original state. So in other words, if liquid water has already turned into gas, you can still change it back to its liquid state. So there is a process called condensation. So you can see here at the top of the arrow. And if you want to change liquid water back to its solid form, the process is called freezing. There are other processes here at the left side of the diagram. These processes, they skip the liquid part of matter. So there are direct changes from solid to gas and gas to solid without passing through the liquid state. So solid becoming gas directly is called sublimation. On the other hand, gas to solid is what we call deposition. What are some good examples of sublimation and deposition? Have you experienced or have you seen frost depositing in a branch? Well, it's not a common thing here in the Philippines because we don't have a cold, cold climate. Our climate is described as tropical. But in some places, example in high altitudes or in the polar regions or near the tropics, frost is a common phenomenon. Frost is the ice that is formed directly from gas. So because this is gas to solid, the process is called deposition. But actually, you don't need to go to those places that I've mentioned. Here in the Philippines, in areas of high altitude, for example, in the Cordilleras, or even here in Bukidnon, or even here in Mount Apo, farmers who have farms in higher altitudes, they experience a phenomenon called frost deposition. And this is very it's not a good news in short for farmers because frost will destroy their crops. Another process is called sublimation. Sublimation is direct conversion or transformation of solid into gas. Have you seen mothballs? Or do you have mothballs at home? In chemistry, we call them naphthalene balls. So do you wonder why mothballs suddenly disappear after a week? For example, if you place mothballs in your drawers or the corners of your room, after a week or after a month, mothballs will completely disappear. What happened to the mothballs? Well, the mothballs, because this is composed of naphthalene particles in its solid form, they directly transform into naphthalene vapor. Since this is solid to vapor or solid to gas, we call the process sublimation. Okay, do you have any questions so far? One good example of sublimation is another thing that we can see at home is our um, comfort room deodorizer or deodorizers. Albatross, for example, is a common brand for deodorizers, and that is the same process for mothballs and deodorizers. We see that albatross deodorizer or deodorizers in general, they will suddenly disappear after a week. Okay, so let's proceed to the next concept. So phase changes, they occur when a substance transitions from one state to another because of energy absorption or energy release. So we have already witnessed from the previous slides the processes of melting, freezing, evaporation, condensation, sublimation, and deposition. You can pause this video if you want to take note of the phase changes happening for every state of matter. So again, as mentioned, heat is either absorbed or released during a phase change. We can see here from left to right the processes of melting, evaporation, and sublimation. Heat energy is taken from environment. So in other words, these processes absorb heat from the environment. On the other hand, condensation, freezing, and deposition, these are processes when heat energy is released to environment. In other words, heat is released from the state of matter to become another state of matter. So energy has an important role in order for phase change to occur. As I've mentioned, energy is either released or absorbed. There are terms that you have to understand when you talk about heat absorption or heat release. For example, generally, we use the term latent heat. This is the hidden heat energy required to change phase, but take note of this without changing the temperature of the object. There are two types of latent heat measures. If you want to measure the energy needed or required to melt a solid into a liquid, then that's what we call as latent heat of fusion. But if you want to measure the energy needed to turn a liquid into a gas, and we call that latent heat of vaporization. So these two measures of latent heat are very important to understand how phase changes occur without changing the temperature of the object. Matter generally will change from one phase to another. The condition is if thermal energy is absorbed or released. We've mentioned it already that latent heat is the amount of energy, in particular heat energy, that is required to change the phase of a substance without changing its temperature. Latent is a word that means hidden. So latent heat means hidden heat. In the SI, we can use units just like joule per kilogram or simply J per kg, per calorie per gram, or small calorie, that's small letter C, not big letter C, small letter C, CAL per G to measure the heat required to change the state of matter. So again, from left to right, solid, liquid to gas, processes that will change from solid, liquid to gas. We've mentioned the name of the process already. All of the processes will absorb thermal energy in order for solid to become liquid and liquid to become gas. Opposite will happen if you want to change gas back to its liquid form or to its solid form. In these cases, thermal energy is released back to the environment. One measure of latent heat is latent heat of fusion. The latent heat of fusion refers to the amount of heat energy required to change a substance from a solid to a liquid state at a constant temperature. The word fusion means melting. So when we say latent heat of fusion of water, this means it is the energy absorbed by water when it melts. So what happens to a solid when it is heated? Example, ice, solid form of water. When ice is heated, its temperature increases until it reaches its melting point. At that point, the substance starts to melt, but take note of this, the temperature remains constant until all the solid has turned into liquid. At that point, temperature already is increasing, but the point where or when the solid arrangement of the particles is transforming into a liquid arrangement, that is the point when the temperature remains constant. The energy required to change solid to its liquid state is what we call as latent heat of fusion. The question is, why does the temperature not changing or not change? This is because the heat energy is being used to break the intermolecular bonds between the particles of the solid rather than increasing the temperature. So the heat that is applied or absorbed in order for solid to become liquid, the heat is not used to increase the temperature. Rather, the heat is used to break the intermolecular bonds between the particles of the solid. So once all the solid has melted, any additional heat energy added will increase the temperature of the liquid. That's the only case. That's the only case when the temperature of the liquid matter already is increasing. It is now increasing because all of the particles in solid form has already broken. Okay? Okay. The other measure of latent heat is called latent heat of vaporization. Latent heat of vaporization refers to the amount of heat energy required to change a substance from a liquid to a gas state at a constant temperature. Remember the word vaporization? Vaporization means changing into vapor. Vapor is one of the manifestations of the state of matter called gas. So this occurs when a liquid is heated to its boiling point or when it is exposed to a vacuum or reduced temperature or pressure, I mean. So both kinds or both measures of latent heat uh, can be plotted in a graph. So these graphs are called heating and cooling curves. Just remember that temperature does not change during phase transitions, and at this point, we can actually measure the latent heat of transformation. So we can see here, this is for water, solid, that is, let's say, sub freezing values, that's below 0 degrees Celsius. Once heat is applied to ice, gradually the formation or solid formation of the particles is being broken into liquid formation. The solid arrangement is now becoming liquid arrangement. So at this point, we can see here the word mix. It means at this point there is solid and there is also liquid state of matter in the object. So ice and water is already mixing at this point, but the temperature is still at 0 degrees Celsius. Once all of the bonds in solids are broken, now that's the time the additional the additional heat energy is now being used to increase the temperature of the liquid state until again it reaches the boiling point of water at sea level, and that is 100 degrees Celsius. And again, we can see here a mixed point. So the point when liquid and gas or gaseous forms of water are already observed in the object. And then lastly, gas. So the plateaus, already I've mentioned, the plateaus in the curve or the flat lines in the curve, they represent phase changes. So for example, from solid to liquid, this is where we can observe or measure latent heat of fusion. The plateau between liquid and gas, that represents latent heat of vaporization. Okay? Okay, in this slide, we can see the values of the latent heat of fusion and latent heat of vaporization for some substances. The latent heat of fusion and vaporization, they are both measured in joule per kilogram. We can see here helium, the first one, then nitrogen, oxygen, ethyl alcohol, water. In particular, I want you to memorize the values for water. Memorize this because I will not allow any copy or index cards with the values written for latent heat and latent heat of fusion and vaporization in those paper. Sulfur, lead, aluminum, silver, gold, and copper. You can pause this video to take note of the following values. Okay, there are many factors that can affect phase changes. For example, pressure is one of the important factor that can affect phase change. So, what's the effect of pressure? Higher pressure increases boiling point. So that means that if we increase the pressure, the boiling point of matter will also increase. That happens, if you notice, that happens exactly inside a pressure cooker. Also, oppositely, lower pressure decreases the boiling point. And that's why we can quickly cook meat inside the pressure cooker because of higher pressure and higher boiling point. What about impurities? Impurities are things supposedly not included in a pure substance or material. If there are impurities, there is also an effect, or they can also affect phase change. Example, if you add salt to ice, it can lower its melting point, and that's why in places that experience heavy pouring of ice in cold places, one thing that they do in order to melt the ice quickly is to pour some salt directly into ice. So this lowers the melting point and the ice will quickly change into liquid state. Okay, so that would be all for today for the phase change. You can review this video, take note of important topics, and also you may ask me directly in our group chat if you want to ask questions related to melting point. And by the way, before we end the lesson, I want you to get a piece of paper, explain how the concept of latent heat helps us understand phase changes in matter. Another thing for the second item, you have to cite two real life examples of each of the following phase change. I want you to cite two examples for evaporation, another for condensation, for melting, freezing point, deposition and sublimation. So that will be all for this lesson. Thank you and thanks for listening.